Hey everyone, it's me, and welcome back to another episode of Physiology 2, again, especially for you. In this video, it will be about respiration, and in particular, we're going to look at the process of saturation. So, saturation is related to the binding of O2 to hemoglobin. In the previous video, we already introduced hemoglobin and where O2 can be bound to. And in this video, basically, we're going to cover steps 2, 3, and 4. 2, 3, and 4 of the entire respiratory process, because we're looking at how O2 and CO2 can actually get into the bloodstream, can be transported through the bloodstream, and also can be released and taken up again at the site of the tissues. So between the tissues, usually the active muscles, and the blood. So if we look at the saturation curve of hemoglobin, you can see it's an S-shaped curve. So the shape is because of the chemistry, but is also connected to the word. Saturation starts with an S, so it's easy to remember. What you can see on the vertical axis is the amount of binding places that are actually occupied by oxygen, expressed as a percentage of the total. And then on the horizontal axis, you can see the partial pressure of O2. And what you see here is that around 40, a PO2 of 40, that is similar or default value for venous content. You can see the saturation is just below 80 roughly. And here you can see that if you look at the PO2 in the arteries, usually of around 100, you can see that the saturation is close to 100%. What you also see from this graph is that upgrading the PO2 even further is not going to upgrade the saturation altogether because of the S-shaped curve. Now, and this difference is marked also in this picture as the amount of O2 that is actually released, for example, at the site of active tissues, muscles during exercise, because if the pressure drops, you can see the saturation drops, which means that more molecules of O2 will be released from the hemoglobin and can actually diffuse in whatever direction needed. So normally the saturation is around 89-99% under normal conditions, and like I said in the previous slide, any further increase is not going to increase saturation. So this is also just one of those examples where you see, or where you could see, that adding artificial oxygen or extra oxygen, for example, to speed up recovery, is basically not really needed. It's basically nonsense because you cannot really push the saturation a lot further. Well, at rest, again, you should know your normal values. So the normal PO2 at rest would be roughly around 40 if you look at the tissues. And you can see also that roughly around 70% of the content that was in the arteries is still present in the veins at rest. So that means your body is not really utilizing a lot at rest, and that is what these values show in a little bit more detail. So the arterial venous O2 difference, more on that later, is calculated by taking 20 milliliters as the arterial content of O2, subtract 15, and that will leave you with an actual utilization of 5 milliliters of oxygen of every deciliter of blood that is passing the tissues. Okay. Now, this AVO2 difference is very important for us later on in exercise physiology. So definitely in other courses like Physiology 3 and 4, we will go further into this variable. But during exercise, usually the arterial content is not going to change too much, but you're actually extracting a lot more, which will be measurable in the venous content of O2, and therefore the AVO2 difference will increase and can definitely increase up to 3 times during exercise, or maybe even more. So how about the different factors that influence saturation? Because that is what really this video is all about. Well, the most important thing to realize is that everything is easily connected to exercise. So from now on, always try and keep exercise in mind, and then all these different factors will hopefully make a lot more sense. The Bohr effect is the actual right shift of the oxygen saturation curve, and the factors that are triggering this Bohr effect are the ones that you can see right here. So an increased pCO2 will actually cause a right shift of the saturation curve. In the next slide, you can see quite clearly per factor what the impact will be on the actual saturation level. But an increase in pCO2, an increase in temperature, an increase in 2,3-DPG, and a decrease in pH level, which is actually an increase in acidity. 2,3-DPG is actually a byproduct of the metabolism that happens within the red blood cells, and all these factors are therefore connected to exercise. So if you exercise, more CO2 is released, more temperature, your temperature will go up, there's more 2,3-DPG released, and there's also more acid released. So all these factors are basically upgraded due to exercise. Just be aware that the pH scale is the inverse of the acidity. So if acidity goes up, the pH value goes down. Well, I mentioned already the 2,3-DPG level, so no need to repeat this right now, but it really helps together with the other factors to get O2 delivered to the tissues, because if those triggers are present in your local muscle, for example, that's very active, they will lower the saturation, which will make the release of O2 from the hemoglobin more easy, and therefore more free molecules are able to diffuse from the blood into the muscle cells for consumption. Now, in these two graphs, you can see basically the exact same shape. The top graph for 2,3-DPG and the bottom graph for temperature. For the example, we're just going to look at temperature. The normal S-shaped curve of the saturation graph is this orange or yellowish graph in the middle. And what you can see is that if you increase the temperature, then you can see that at any given pressure, there's a lower saturation. So for example, if we take this pressure here, there's a lower saturation than at a normal temperature. So what that means is that if you increase temperature, which is likely during exercise, the hemoglobin wants to release more of the molecules to make them free, and that will allow more free molecules to be able to diffuse into the cells. The opposite will happen if the temperature goes down. So if the body gets cooler, you see that the binding actually is more easy, and that will then increase at any given partial pressure the saturation. So more binding places out of the total are occupied in colder conditions compared to warm conditions. For acidity, again, the graphs have a slightly different shape, but the whole idea is the same. So the Bohr effect is actually the pink line, or sorry, the purple line that is a right shift compared to this yellow/orange line. All right, so a high acidity means, again, at any given pressure, the saturation drops of hemoglobin, which will release more free molecules of O2. And that's it. Now, myoglobin, I mentioned it in the previous video, is actually the little brother of hemoglobin. Similar structure. It has 1 compared to 4, 1 iron molecule for the binding of O2, and you can see it in skeletal muscle or cardiac muscle, and it just makes sure that you can actually store some of your O2, and then from the myoglobin, the oxygen can be released and diffuse into the mitochondria. For CO2, we have different transport mechanisms. We actually have 3. The first one is that CO2 can be bound to hemoglobin in a different way than oxygen can. It can be dissolved into the plasma, and it can be part of what we call the bicarbonate buffer, and that's something that we will see in one of the next slides. The free amount is roughly 5%, and that again determines the partial pressure of CO2 inside the blood. So again, the percentage is low, but the significance is high. So here you can see an overview of the CO2 being produced, and you can see in which directions literally the CO2 can go into. And this is what we call part of the bicarbonate buffer. More explanation on this in the next slides. So what you see right here is the CO2 produced in your muscle cells, for example, getting into the bloodstream, whereas here you see the CO2 from the bloodstream diffusing out into the alveolus and then moving out to the atmosphere. Now, what I mentioned already, the bicarbonate buffer is basically this formula right here. And that is one of the most essential formulas also later on in the respiratory physiology, especially if you look at exercise. So what you see is that there's a chemical equilibrium between CO2 and water and what we call carbonic acid, and then ultimately bicarbonate and acid. Now, in chemistry, the equilibrium is usually both ways. So the equilibrium can go left and the equilibrium reaction can go right. Now, CO2 plus water can be converted into acid, but also the other way around. So for example, during exercise, you can see that this is a way for the body to buffer the amount of acid in the blood, because if you take away something on the left side of this equilibrium reaction, and CO2 can be lowered just by expiring more CO2. If you lower a value on this side, you will automatically pull the whole reaction into that direction. So by changing CO2 levels by ventilation, this buffer or this equilibrium reaction actually allows you to regulate acid levels indirectly. The other example of transport, or the other method of transport, is that it can actually bind to hemoglobin, but again, not in the same binding places as O2. And this is also for the CO2 to be transported again back to the lungs so that it can be expired. And the Haldane effect is an interesting factor that again makes sense if you think about exercise and what the ventilation is supposed to do, especially if you have a lot of O2 that is being bound to hemoglobin, that will automatically release CO2 from other binding places, and that is literally what is needed inside the lungs. If you take more O2 into the blood, then at the same time you want to get rid of CO2, so that's what this method allows your body to do. Finally, before we close this video, a very important remark that you should never confuse carbon monoxide with carbon dioxide. So carbon monoxide is something that can be produced in old heating systems, for example, that have incomplete burning of the fuel. And then instead of just regular CO2, you could actually have CO, carbon monoxide, produced. And that is very, very dangerous because CO actually wants to bind to the exact same binding places as O2 on the hemoglobin molecule. And that's the reason why your body doesn't realize it's actually not O2 that is bound to hemoglobin, but it is carbon monoxide. And especially because of the affinity that is a lot higher, it's quite dangerous because your body is not going to notice until it's already too late. So unfortunately, still nowadays you will see every now and then an example on the news where you see that someone either died or at least was seriously affected by carbon monoxide poisoning, and that is literally because of the saturation that is actually recognized as 100%, for example, by the body, but that is done because of the carbon monoxide, and that basically means your body has no O2 to transport, and actually you have a big problem. All right. That was it for this video. I thank you again for watching, and I really hope to see you in the next one. Bye-bye.